Welcome back to our next part of our lesson in the ozone chapter. We're looking at atomic structure and periodicity in our second section. It begins with a topic called atoms, those basic building blocks of matter, the smallest particle of matter in which we put together to build larger compounds from. And just a little crash course perhaps from elementary school, you remember that atoms exist in building blocks, and so inside of a nucleus we have protons and neutrons. I like to just denote protons as little p positives, reminding me that protons are positively charged particles inside the nucleus of an atom. And then I like to denote neutrons as little n's with a 0 written after it to remind us that neutrons are neutrally charged. Protons are found in the nucleus and are these positively charged pieces. Neutrons are found in the nucleus, but they carry no charge. And then orbiting outside of the nucleus, kind of these energy rings, we know to be these particles known as electrons. I denote electrons with little e negative to just remind me that electrons carry a negative charge. Positive protons, and we have neutral neutrons, and we have negative electrons. Protons and neutrons in the nucleus of the atom, and then again as we create these energy rings going around the atom, we start to place the electrons outside in these orbiting fields. When we look at the arrangement of atoms, the periodic table gives us great insight into what's building the components of a specific element. On the periodic table, I know that this particular chapter focuses on oxygen, so I look at the table and find the element oxygen. And if you have your periodic table nearby, perhaps it looks something like this slide here. Notice where oxygen is on the periodic table. It has an elemental symbol of just a capital O. I notice that its words are written under here for the name oxygen, and I see down below its mass number of 15.999. I see a value number 8, and I see a 15.999. So when I carried that over to this particular slide, I rounded a little bit and said the mass number is 16.00 and its atomic number is 8. The atomic number, by definition, tells me the number of protons inside the nucleus of this atom. So if I were to consider drawing just a rough model of our oxygen atom, I now know that it has 8 positive protons inside of the nucleus of that atom. By definition, the atomic number gives me the number of protons inside the nucleus. The other value found in that box is the mass number of the element. The mass number comes from 2 pieces of the 3 subatomic particles. The weight of the atom is found in the nucleus. The nucleus consists of protons and neutrons. If the total mass is 16, and 8 of those pieces are accounted for already by positive protons, the total number of 16 minus 8 leaves me a remainder of 8 neutral neutrons. So in the nucleus are 16 total particles, 8 of which come from protons. The other 8 must come from the neutrons. Now, since atoms are electrically neutral, and what that means is that the positives have to equal or balance out the negative charge. So what I've also learned is when I soon found out by the atomic number oxygen has 8 positive protons, I also know that I also know that instead of a plus sign there, I wanted to say equals 8 electrons. The positive charges must equal or balance out the negative charges because atoms overall are electrically neutral. And so I can feel that the positives and the negatives will balance to be 0. So 8 protons also tells me that I have to arrange 8 electrons around in a very ordered fashion around the nucleus. So let's examine that periodic table and see what we remember. Hydrogen is in our first period. Rows going across are known as periods. The first period consists of two elements, hydrogen and helium. And then I hit the end of the row. In the very first energy level, I have up to 2 electrons, and then it's full, because hydrogen and helium represent the first 2 electrons in the electron arrangement, and in the first energy level, there's only 2 positions. So to carry that here, in my first energy level, and friends, I'm just going to write out a half shell, and in your mind, you'll notice that you just have to visualize I'm going all the way around the nucleus. I just don't want to take up that space. I'm going to put the first 2 electrons of the 8 I need in that first energy level. And again, to repeat, period 1 has 2 elements, hydrogen, helium. Then it's done. Row 1 is complete, up to 2 electrons in the first energy level. Then I hit row 2 on our periodic table, period 2. I have lithium, beryllium, boron, carbon, nitrogen, and then oxygen. Notice oxygen is in the 6th position in this particular row. Its group number is 6A. Group 6A tells me the position or what column oxygen is found in. And to get to oxygen, I only went over 6 more positions. So in row 2, that's our second energy level, I had 6 more electrons to place. 2 plus 6 gives me the total of 8 electrons. This is a very, solar system type model of an atom, looking at a basic structure of protons and neutrons in the center, and then electrons begin to arrange themselves outside. And perhaps from some earlier days and earlier lessons in your high school, whatever it might have been, you remember that the second period has 8 elements in it: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Those are 8 positions, and so therefore only 8 electrons in the second energy level. When you get to row 3, there are 8 more: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Those are 8 more positions, so the third energy level can hold up to 8 electrons. And I bet the biggest one I'll ever ask you to draw would be like calcium's 4th energy level, 2 in the outermost shell. And this is just really reminding us why atoms live where they live on our periodic table. All has to do with their electron configuration. How do they arrange their electrons outside of the nucleus? And so in the nucleus, we have protons and neutrons. The nucleus gives us the mass of the atom. The 2 pieces together will weigh the total sum of the element. The electrons arrange themselves outside of the nucleus in a very ordered fashion related to what period and group number that they live. The number of shells we drew related to the period that they lived in. Oxygen lives in period 2. We drew 2 energy levels. The outermost electron arrangement came from the group number. Oxygen lived in group 6A. We drew 6 electrons in its outermost energy level. We'll soon see a vocabulary word for that. Those outermost electrons are known as valence electrons. And for a chemist, that's what we're interested in, are those outermost energy levels. Lots of good information on this slide. And as we kind of just continue reminding ourselves, we have periods on the periodic table. And we have group numbers, group 1A, 2A, next tall column, 3A, 4A, 5, 6, 7, group 8A. The tall columns on the outside we've learned are called representative elements. And we've also learned that the shorter elements in the center are known as group Bs, and the group Bs are known as transition metals. So what might a practice with this skill look like? Using your periodic table, let's just practice a little bit. Specify the protons, neutrons, and electrons and drawing a simple model for each of the following elements: carbon 12, calcium 40, and chlorine 36. The little number here next to the name is giving us the mass number for the element. So if we were to consider carbon, whose elemental symbol is C, capital C for carbon, it lives in group 4A in period 2. So what that's telling me is I'm going to end up drawing 2 rings, 2 shells to place those electrons in, and I bet the last one will contain 4 electrons. The other number, while we're here, just to help us with vocabulary, is its atomic number. Its atomic number is 6. Mass number 12, atomic number 6. So if I consider what we have here, I know that it has, and I'll put it up here, I guess, 6, and then underneath it I'll write 12.00, just to kind of remind us how we found it on the periodic table. So by definition, we know that this 6 is called its atomic number, and this 12 is known as its mass number. So a very simple model for carbon would place 6 positive protons. The atomic number tells me protons. 12 minus 6 leaves me 6 neutral neutrons. All the pieces added together in the nucleus add to 12. If 6 of those pieces are accounted for by the protons, the remainder is 6 more for neutrons. Atoms are neutral. That tells me that the number of protons also will be the same number as electrons. I know the first energy level can hold at most 2 electrons and then it's full. To remind ourselves why, the first energy level represents the first period on the periodic table. There's only 2 positions in that first period. A maximum of 2 electrons fills the first energy level. Then we add a ring. 1, 2, 3, 4 positions to get over to the carbon. Notice its group number is 4A. There'll be 4 more electrons in our model. Second energy level, 4 more electrons, giving me a total of 6 to balance the electrical charge of the 6 positive protons. And just to help us remember a vocabulary word, the electrons in the outermost energy level are known as the valence electrons. The number of valence electrons comes from the group number. Carbon lived in group 4A. There were 4 electrons in the outermost shell. The period told me how many energy levels I was going to have to draw. The period that carbon lives in is period 2. We drew 2 energy levels with the electron configuration or electron arrangement of 2, then 4. Shall we try a calcium? Calcium has an elemental symbol of Ca. It lives right here on our periodic table. It's in period 4, group 2A. We will end up drawing 4 energy levels, 4 rings, and in the last ring we are going to place 2 electrons, and I bet by the time we're there it will add to 20. Calcium has an atomic number of 20 and a mass number of 40. So by finding that information, we said its atomic number was 20 and its mass number was 40. So if we start drawing, we would have in the nucleus 20 positive protons. I know that because of the atomic number. By definition, atomic number tells me the identity. It gives me 20 positive protons. 40 minus 20 leaves me 20 neutral neutrons. So the sum of all the parts in the nucleus is the mass number of 40. In the first energy level, we know to place 2 electrons. We know the first energy level can hold 2 electrons because there's just 2 elements in the first row. In the second energy level, we said there were 8 more elements, all the way from lithium to neon. Group 1A through 8A adds 8 more electrons in the second energy level. So I pass through that row and add those 8 electrons into our model. So in a second energy level, I'll add 8 electrons. The same will be true in the third energy level, 8 more electrons. See where we're at so far? We have 10, plus 8 more is 18. We need 20 to balance that proton charge. That leaves me a remainder of 2 to get the 20 electrons we needed to balance protons. So again, using your periodic table skills, calcium was row 4, 4 shells. Group 2, 2 electrons in the outermost shell, and that would add up to 18 by the time we went 2, 8 more in the second energy level, 8 more in the third energy level, 2 more, and we've arrived at calcium. There was one more in our practice. It was for chlorine. Chlorine is number 17. But let's get the better information as well while we're here. Chlorine lives in period 3. I bet that'll have 3 rings. And it lives in group 7A, so there'll be 7 valence electrons in that outermost energy level. So if we practice one more together, chlorine, number 36, and just drawing a simple model of what it would look like. Let's give ourselves some room. We said chlorine was number 17, and we were going to draw for the mass number of 36. In the nucleus, such a great artist, 17 positive protons. By definition, the atomic number tells me the number of protons. What's 36 minus 17? That's 19. I need 19 more particles in that nucleus to create a total mass of 36. 36 minus 17 left me a remainder of 19 neutral neutrons. We said chlorine lives in period 3. First energy level can hold up to 2 electrons. Second energy level can hold up to 8 electrons. There's 10 so far. And we knew, based on the position where chlorine would live, there would be 7 more electrons to place in that third energy level. This is known as a valence electron, the electrons in the outermost energy level. These are what are interesting for a chemist because they're the electrons that are going to be involved in bonding. Good work. So we've explored some of the information we can find on the periodic table. We know that it's just a table that lists the elements in order of increasing atomic number. So all that's saying is hydrogen 1, helium 2, lithium 3, beryllium 4. As I move from left to right, I'm increasing the number of protons in the nucleus of each atom of the various elements by 1. So the integer just simply increases from left to right, 1 at a time. The table also has elements arranged with the similar properties falling into the same column. And this is simply due to the electron distribution in that outermost energy level, that vocabulary word I've been saying, those valence electrons. So any element found in this first column lives in that first column because it has just 1 valence electron, group 1A. Every element in this column has 2 valence electrons. It does so because it lives in group 2A. Keep going to the representative elements. Everyone in this third tall column, group 3A, has 3 valence electrons. Carbon's family has 4 valence electrons. Nitrogen's family, 5 valence electrons. Oxygen's family has 6. Fluorine's family has 7. And not helium, because helium only has 2 electrons. But everybody under helium, neon, argon, krypton, xenon, radon, they all have 8 valence electrons. The noble gases. So the periodic table starts to arrange these elements in columns because they have similar characteristics because of the valence electron shells. And that's what this table from your book is reminding us. And these arrows didn't line up very well. Group 1A is this first column, all having one valence electron. Group 2A all have two valence electrons. Group 3A, 4A, 5A, 6A, 7A. Remember, helium only has two, but everybody under helium all have 8 valence electrons. In some of these families, they have special names given to them, and they do so based on the reactivity. And at this time, I know in our Blackboard shell, I have placed some interesting chemical demonstrations for each of the families. It would be awesome if you would take some time to just watch interesting demos of some of the reactions that each of the family members are involved with. So when I tell you that the alkali metals are highly reactive, I want you to see some of those. You'll see the luster, which is shininess. You'll see the reactivity with not only just oxygen from the air, but they're going to drop those alkali metals into water. It's pretty cool to see. So at this time, it would be very helpful if you paused this video lesson, went in to find those alkali metals, alkaline earth metals, which are group 2As. Watch that video clip. It's just here to see some interesting periodicity of the alkaline earth metals. Also watch the halogens, which is group 7A, fluorine, chlorine, bromine, and iodine. I'm going to show you some reactivity there. And the last little clip I want you to watch is the noble gases, and it's pretty interesting because they have them all in balloons. You're going to just take a look at their density. So pause the video and watch the reactions for each of these chemical families, and then come back to this video lesson when ready. Welcome back. So you've had a great opportunity to kind of get familiar with some of the actions of the certain chemical families. So to remind yourself what you've just watched, lithium, sodium, potassium, rubidium, cesium, these are known as the alkali metals, all with one valence electrons. Made them pretty darn cool to watch, didn't they? Beryllium's family, these are the alkaline earth metals. You watched the halogens, which is fluorine's family, group 7A, and you watched the noble gases with their demonstrations, group 8A. Those are names given to different families on the periodic table. Let's practice. Using your periodic table as a guide, specify the group number and the number of outer electrons in a neutral atom. They're going to be the same, aren't they? Let's find sulfur on that periodic table and see if we can't use our periodic table to figure out how many valence electrons sulfur has. So you notice here, this is where sulfur is. Atomic symbol is S, capital S. It would have 6 valence electrons because it lives in group 6A, 6 valence electrons. I think it's here. Silicon has the atomic symbol Si, and we're going to look for nitrogen and we'll look for krypton. So sulfur, we said, lives in group 6A, so therefore it has 6 valence electrons. Pulling up for sulfur. Now silicon, here's the symbol for silicon, lives in group 4A. Nitrogen, who lives in group 5A, and krypton, who lives in group 8A. See these symbols? Krypton, Kr, nitrogen, N, and Si for silicon, and we had looked up sulfur. So I'll grab those all at once just so I don't have to keep flipping back. We said silicon lives in group 4A, so 4 valence electrons. Nitrogen, who lives in group 5A with its 5 valence electrons, and krypton, who lives in group 8A, had 8 valence electrons. So what might some of your sapling questions look like? We're going to be given the following isotopes, in which is just a variety of the atom. Complete the table. We're given the elemental symbol, a mass number, the number of neutrons, the number of protons, and the number of electrons. Whatever it is in the boxes that is missing, it's our job to fill them in. So let's start here. We're going to find the symbol Se on the periodic table. So let's find Se and what information we can pull from it. Se is for the element known as selenium. Selenium lives in period 4, group 6A, atomic number 34. See what I've done? Period 4, that's the row it's in. Group 6A, that's the column it's in. And 34 is its atomic number. As soon as I know the atomic number, I know the number of protons to be 34. I know the number of electrons must also be 34 because atoms are electrically neutral. If the entire atom weighs 76, that's the mass number, and 34 of those pieces, remember this is mass number, is the sum of protons and neutrons. So we're going to subtract out the number of protons. We get 2 and 4. We get 42 as our number of neutrons. Let's look at row 2, or column 2. We're given a mass number of 65, the sum of both particles, and if I subtract the number of neutrons, which are 36, we get 9 and 2 when we subtract. So that tells me that those must be the number of protons because the sum of these two pieces must be 25. And as soon as I know this, 29, I know it's automatically the same for electrons. And now who is element 29? To identify it, we use our periodic table and go to work to find number 29. And on our periodic table, number 29 is the element copper. And so its elemental symbol of Cu needs to be placed in the box there. How you doing? Is this easy? Here we're given the number of neutrons and the number of electrons. So as soon as I know the electrons, I also know it's the same number as protons because atoms are neutral. I can add 47 and 36 to get my mass number because the sum of protons and neutrons added together gives me 83. And the identity of the element comes from its protons. That's number 36. Who is number 36? Number 36 on our periodic table, right here, krypton, with the elemental symbol of Kr. And so that would finish that particular sapling question. We would have to just simply place the symbol for krypton in that box. You're doing well. Same idea, duplicate slide. What sort of elements would most likely exhibit similar chemical properties? It doesn't matter which pair they go in. So I think this sapling is saying what we want to do is place two elements that have similar properties into the boxes. And remember, the properties are going to come from being in the same family or same group, same column on the periodic table. So let's just put in arsenic into the first box. All right, so let's just find out of these other choices who is in the same column as the element arsenic. So here's As, arsenic. We see the family belongs to group 5A, nitrogen, phosphorus, arsenic, antimony, bismuth. All of these elements would have similar properties of arsenic. So out of the choices we were given, do you see anybody in the same column? I do, right here, the nitrogen. Because they both live in group 5A and it won't ask you to type that in. But that's the reason I lumped those two together, is because they both live in 5a. They both have 5 valence electrons in their outermost energy level. So we've used those two elements up. For no other reason, let's go next door. Let's put barium. The elemental symbol Ba stands for the element barium. And if you find barium on the periodic table, barium is way down here. It's in the second column. We would call that group 2A. Beryllium, magnesium, calcium, strontium, barium, and radium. Who would have similar physical and chemical properties as the element barium from the list we were provided? Do you see any that are in the same column as barium? I do right here as well. It's the element calcium, also in group 2A. And then we could verify that helium, elemental symbol for helium, He, and argon, the elemental symbol for argon is Ar. Both of those families, or both of those elements, live in the same family. Very over here, helium and argon belong to the noble gases. So we decided that elements that live in the same column have similar properties because they all have the same number of valence electrons. This only has 2, but it belongs to group 8A. Just want to clarify. You're doing so well. How many electrons in the outermost energy level do the following atoms have? Well, this is asking you the same as the other slide, just a little bit different. It wants to know what group number these elements live in. The number of outer shell electrons, which are called valence electrons, simply comes from the group number that they live in. We have krypton, gallium, nitrogen, selenium, and cesium. We're going to just type in a number into your sapling assignment, where the number represents the number of electrons. So for instance, with krypton, I think we found that one earlier. The symbol is Kr. Krypton lives right here, group 8A, 8 valence electrons. I think I remember cesium here, group 1A, and so forth. So just a little heads up on the directions, and you can go to work finding the group numbers. We found krypton lives in group 8A. I found cesium living in group 1A. And I'm just going to put the group number, not the letter with it, but just the number of electrons in the outermost shell. And you're going to do that by locating where it lives on the periodic table, looking up at the column. We want to know the family or the group number. Here's something kind of seeding the next section called Lewis dot symbols, and perhaps you remember these from earlier science classes as well. Electron dot structures, or sometimes named after the person who developed this system, is Lewis dots. The little symbol, and this is just a generic symbol for any element with a symbol X. There is no symbol, just X, but we can represent any element with a symbol X. And I notice that it has 1, 2, 3, 4, 5 dots. Those dots are representing something known as the valence electrons. And so if I want to know what element could possibly be represented with this symbol, the 5 dots representing the 5 valence electrons, this question is really just asking me who lives in group 5A. Of all the list here, can you find an element that lives in group 5A? Remember where that is on our periodic table? Group 5A is nitrogen's family. I would select nitrogen or phosphorus or arsenic, antimony, or bismuth, the naturally occurring elements. Any of those would have 5 valence electrons. And so of all the elements listed in our example here, who had 5 valence electrons? I saw nitrogen. I think boron, that's group 3A. Nitrogen is 5. Fluorine is 7. Calcium is 2. Carbon is 4. Oxygen 6. Neon 8. Sodium 1. Just sharing with you what group number each of those live in. The only one who lives in group 5A is nitrogen. So these Lewis dot symbols are kind of interesting in helping us write out the valence electrons in our atoms. Let's introduce a little bit more about a word we read in these questions called isotopes. Isotopes are two or more forms of the same element, same protons, same electrons, behaving in exactly the same chemical way. They just differ by the number of neutrons. So the atom's weight is a little bit different from one isotope to the other. Remember, isotopes have the same atomic number. When I find carbon on the periodic table, remember carbon? I have to keep sliding up. Carbon is number 6, right? Number 6. It has 6 protons. If it didn't have 6, it would be a different element. If it had 7, it's not carbon anymore, it's nitrogen. If it had 5, it's not carbon anymore, it's boron. So all the forms of carbon that we find in nature have 6 positive protons. That's a given. By definition, carbon has 6 positive protons. But what may be different from one form of this atom to another that we find in nature, the different isotopic forms we find of carbon, are the number of neutrons. In this particular carbon atom, I would have 6 neutral neutrons. In this particular carbon atom, I would have 7 neutral neutrons. And in this particular carbon variety, I'd have 8 neutral neutrons. By changing the number of neutrons in the nucleus, the atom weighs different, but it does not change the behavior of that particular atom. It's still just carbon, weighing just a little bit differently. And so when I look at carbon 14, we said it has 8 neutrons, but it had 6 positive protons, and it had 6 electrons. The atomic number told me about 6 protons, 6 electrons, and I subtracted to find the number of neutrons. What about in uranium-235? The elemental symbol for uranium is U, and they're telling me the mass number is 235. What I don't know by heart is the atomic number. Uranium, down here in the very bottom row, is number 92. So it's the last naturally occurring element. Number 92 is known as uranium. So once I find its location, I know the number of protons because its atomic number, 92, told me so. So as I come down here and want to find where we left off, uranium with its number 92 tells me protons and electrons. So what is, all right, we'll put 92 positive protons, 92 negative electrons, and I'm going to need to subtract to find the neutrons. Looks like 143 neutral neutrons. So just to practice again, what we're doing is finding the atomic number by location on the periodic table, and that right here, the atomic number gives me these two species, protons and electrons. They come from finding the location and seeing what its atomic number is, protons and electrons, because atoms are electrically neutral. And the neutron comes from the difference of the mass number minus the atomic number. So again, mass number minus atomic number found the number of neutrons. You'll want to pause your video here. You've done a great job. This was all in the second section of our Chapter 2. When ready, come on back for the next part of your lesson, looking at molecules and models, looking a little closer at our Lewis dot structures.